We're going to finish off this unit by talking about heating curves, and where we're going to take pretty much everything that we've learned up to now and kind of quantifying some of the energy that's associated with it. So rather than think of it as just kind of energy in, energy out, we can actually calculate how much energy is either going in or going out. To start, let's go ahead and find that there's a difference between heat and temperature. So the two we often, very often anyway, conflate with each other. But in the technical language, let's actually make sure we know the difference. So when it comes to heat and temperature, first of all, temperature is what we discussed before. This is basically a measure of the kinetic energy of the particles in your sample. So high kinetic energy means high temperature, or low temperature means low kinetic energy of your particles. Your particles are not moving very quickly. Whereas heat is actually more of the flow of energy. So we actually know that there's going to be some amount of change in energy from one substance to another. More specifically, you should know that heat will always flow from high temperature to low temperature, right? Because if you think about it, right, we have high kinetic energy when we have these high particles or high temperatures, and over here we have low kinetic energy when we have lower temperatures. And so that's basically the difference between something that's moving very quickly, right, versus something that's moving very slowly. And that range of motion, or like that, is the differences in kinetic energies, they're going to actually, again, collide with each other. The particles sort of bounce around and collide with each other, to where the hotter ones, the faster moving ones, the higher kinetic energy ones, will collide with the cooler particles, the slower moving particles, the ones with the lower kinetic energy. So, for example, when you have a hot block of metal, it's placed into a cool glass of water. All right, so we'll have ourselves a little diagram here. We got a glass of water. We have a hot piece of metal, which we represent with red. And what happens then is that energy is going to flow out of the piece of metal into the water. And that's where because the temperature of the metal is hotter than that of the water. Eventually, though, we're not going to really see that this heat transfers for infinity, right? It doesn't happen for forever. It eventually stops when the temperature of the metal and the temperature of the water eventually equal. You can look at this analogy underneath it, talking about a sort of basically talking about moisture and water when it comes to towels, having a damp one versus a wet one, in a sort of a casual, loose analogy to heat and temperature. How we can quantify heat. There's a couple things we need to discuss here. First of all, the symbol for heat, the actual thing we use is a lowercase q, which we'll see more often than the capital Q, which you might see from time to time, but definitely lowercase q is the way to go. So if I ask you, hey, how much heat is transferred, you'd be giving me an actual value where Q equals something. The units for heat is joules. We've probably seen this before, right? So the unit for energy, it's a capital J. And sometimes you might see calories as well, but the one that we'll be using most often is joules with a capital J. You also notice that you have some comment here about how food calories, these are actually not, the same calories that we have up here. Food calories, the ones you see on the back of nutrition labels, those are actually kilocalories, and oftentimes abbreviated with the capital C. So really when you say 1 food calorie, right, this food item has 100 calories in it, really it's saying you have 100,000 of these calories in there. Finally, on this slide, the sign of Q is important. This helps us know information about whether heat is gained or heat is lost. Because if Q is negative, that means a substance, whatever it might be, has lost heat. So going back to the example from the previous page, where you have yourself this water and you have a piece of hot metal, right? The value of the Q, the heat that the energy that this block of metal lost, that would be a negative sign. So you can see here, whoopsies. I wrote some stuff in there. So you see here, the Q of the metal, right, that is going out, so that would be a negative value. All right. Notice how I also have Q and then have a subscript here for metal, or it's in sort of subscript words. Metal, it's a little sloppy, but you get the idea. And then Q of H2O, so the water that's surrounding it, that's going to gain that energy that the metal lost. And that Q of H2O, that will actually then be positive. Let's talk about another term. This one's related to heat, but it's not exactly the same thing. And it's kind of a little confusing because it does share a word. This is called specific heat. Often, actually, it really should be called specific heat capacity, but we usually shorten it down to specific heat. The definition here says, the amount of energy required to increase 1 gram of a sample by 1 degree Celsius. So different samples will have different various specific heats. So this is a concept or a value that is specific to the substance we have here. It will change depending if you have water, or if you have ethanol, or if you have gasoline, or if you have iron or gold. Each of those substances has their own specific heat capacity, also known as specific heat. In a way, you can kind of say it's specific to the substance. I suppose that's what that word specific means. But it's not like heat as in, we have energy that goes in or out. It's actually a kind of an energy per something something. So it's a little bit more specific to the substance and the temperature involved. Now, effectively, this can be thought of as the resistance to change in temperature. So when you have two different substances, let's go ahead and say we have water. All right, let's say this water is, again, represented by this random block. And let's say we have 1 gram of this water. And then let's say we have another metal. Let's say it's going to be iron, right? This is going to be 1 gram of iron. Both of these, again, are having the mass of 1 gram. We're going to input some energy, right? So energy, we'll just, use some kind of here. So energy goes in, energy goes in, energy goes in, energy goes in. So what happens is that the amount of energy required to change 1 gram of water is going to end up being a lot more than 1 gram of iron. You can imagine this, right? If you took a pot, right, that's usually made of metal, some sort of a steel, which has a lot of iron in it. You take some metal and then you apply some heat to it. That metal is going to heat up very quickly. Right? It doesn't take a lot of time. But if you took that same flame, took some heat to it, to some water, though, the water actually is not really noticeable that the energy would have caused a temperature change. And that's because the inherent properties of metal and iron, or iron and water, are very different, so that water can actually absorb a lot more energy but not change temperature. Metal can absorb the same amount of energy but change a lot of temperature. It'll increase by temperature by quite a bit. And that kind of matches what you see over here. So let's go and use these as our highlighted values. It might be kind of small, so I'm going to zoom in just a bit. So for example, liquid water has a value of 4.18, and then iron has a value of 0.449. Right? So those values, again, by themselves don't mean a whole lot, but really just think about it. If you have a higher value for a specific heat, that means more energy is required to be added in order to increase that sample by 1 degree Celsius. Iron, however, is 0.449. That's how much energy it takes to increase 1 gram of iron by 1 degree Celsius. And again, the same idea, right? I'm adding in these little purple arrows here, pink arrows. That's the same amount of energy, and yet this water will maybe only increase by like 0.05 degrees, right? Just making up a number here. Whereas this one might increase by like 10 degrees Celsius, just making up some numbers. But you get the idea. So ultimately, when you look at these specific heats, it's helpful to, one, be able to know how to compare them and sort of justify it in the way that we talk about metal versus water, kind of conceptually, right? You have the intuition of knowing metal versus water, which one's going to be able to be more resistant. But also just kind of knowing that the value of the units and so on and so forth, while not important, tells us that information. It's actually pretty consistent. So again, think of specific heat as the resistance to change in temperature. Couple of other notes. You'll see that the symbol for this is C, right? Capital C. Even though it looks like it might be degrees Celsius or a Celsius measurement, it's actually not, right? So it's just C. And then the units are joules per gram Celsius. At least that's the one that we'll use. There are a couple other variations, but the one we'll most often see is joules per gram Celsius. And yes, it is the entire unit of joules per grams times degrees Celsius. And all of grams times degrees Celsius is on the denominator of that fraction. So that entire thing is the units for specific heat. So we can actually calculate heat as well. There's ways that we can quantify that amount of energy. So we're going to use this formula Q equals M times C times delta T. So these are the three factors. Mass, that's C, which was the specific heat from the previous page, times this delta T, which we'll talk about more in a little bit, which is the change in temperature, is equal to Q. And that Q that we were asking about a minute ago, saying, hey, how much energy does it take to change something by a certain temperature? Q is that amount of energy. That tells us how much energy it is. So you have these three terms. You can see it's all broken down. Q is that amount of energy transfer there is. That's going to be units of J. Mass, M, no problem there, grams. C is in joules per gram Celsius. We just covered that in the previous slide. And then delta T is that temperature change, which will be in degrees Celsius. Delta T, right, this is that Greek letter delta. This, anytime you see this, generally means change. But more specifically, it's almost always going to be a final amount minus an initial amount. So there's kind of some embedded concepts in this delta T. Make sure you recognize that it's always going to be the final minus the initial amount, which is equal to that delta T. Right. So we're going to apply this on the next slide to be able to know how to use this expression. So when it comes to this example, go ahead and take a look and identify what they're asking for and then what you're given. It says 10.0 grams sample of liquid water. Warms from 45 degrees to 60 degrees. What is the amount of energy absorbed by the water? Okay, so first of all, they're giving us a mass of this liquid water, right? So we know we're talking about mass, or sorry, talking about water. We also have 45.0 degrees Celsius, and that looks like a temperature change. Well, it got to be specific. It's not just temperatures. Let's go and identify if they're initial or final, or warms from this to this. This is going to be my final temperature. This is going to be my initial temperature. They're asking what is the amount of energy absorbed by the water. So they're asking for, effectively, amount of energy, which is Q. All right, so what is Q? I'm going to use that expression Q is equal to M times C times delta T. I'm going to leave off those multiply signs. You get the idea. And try this one more time. What do we know we have? We have mass. We can kind of get delta T. You can kind of see where this is headed to get delta T. But then what about C? Well, again, C is a specific heat. It's specific to the substance. Well, liquid water, let me go and tell you this one right now. You go ahead and commit this one to memory. It's going to be 4.184, those are numbers, joules per grams degrees Celsius, right? The specific heat of water. So we basically always have that available to you. That's one that you'll just have to memorize because we use that quite a bit. And then, of course, we're solving for Q, so basically we can just plug all the numbers that we have in here and then figure it out. Before I can plug some numbers in though, let's go ahead and figure out what delta T is, just so we have an idea of how to do this. So delta T is equal to 60.0 degrees Celsius minus 45.0 degrees Celsius. Notice how I'm leaving in all the decimal places as the original numbers are represented because you don't want to lose that significance. You do some math here and you'll find that this will be 15.0 degrees Celsius, not just 15. Let's plug those numbers into your formula. So Q is equal to the mass, which is 10.0 grams, times the specific heat, which is 4.184 joules per grams degrees Celsius, times delta T, which is 15 degrees Celsius, which is what we solved for over here. Now, one thing we need to do, just double check that all the units work out. Make sure that you know this has to be in grams, right? Because when you look at these, the units sort of have to work out. Grams are here, grams are here, right? So make sure those units are consistent. You're going to end up having degrees Celsius here and degrees Celsius here, so those units again have to be consistent. So if you have any other non-degrees Celsius or grams units, you need to change them into the appropriate one. And then finally, when you do all the math, right, you cancel off some stuff, you end up getting joules as your unit left over. So when you go ahead and plug this into your calculator, you end up getting 628 joules, right, because there's three significant figures. This is a constant, so it's infinite. This shows three significant figures, and so you get 628 joules. The second problem is a similar setup, but it's got a little bit more work to do. Let's find out what we have to do. What is the final temperature of, no, words are missing there, 100.0 grams of water that has an initial temperature of 45 degrees Celsius and released 87 or 8.71 kilojoules of energy? Okay, let's try to break this one up. What are we given? All right, we're given a mass, right? We have an initial temperature, and it releases this amount of energy. So we basically have some amount of Q, some amount of energy that was transferred. An important thing to know also is that they do tell us water, so that tells us that we have a specific heat as well. That's a value that we can just know. And like I said, go and commit this one to memory because we use it quite a bit. So what do we do here? Well, let's plug in what we can. Rewrite the Q equals MCAT just so we can keep track of what we need to know. We're actually given a Q this time, so I'm going to go ahead and check that. We're given a mass, and we're also kind of given a specific heat, right, just because you know it. But delta T we don't have. Remember that within delta T there is a final minus initial. So we actually, again, kind of have almost all of it. We do have an initial temperature, but we don't have a final temperature. So we need to solve for that final temperature right there. How do we do that? Well, let's go and plug numbers that we can into the formula. Remember that the units always have to be consistent when you plug them in. And what do you notice about the energy units? Well, it's in kilojoules, lowercase k. That's a prefix that we have to convert. So let's see how this works. Let's go ahead and do 8.71 kilojoules. We're going to convert that into joules. Why? Because our specific heat is in joules per gram Celsius. So for every 1 kilojoules, you have 1,000 joules, and that ends up being 8,710 joules of energy. That's our Q. Let's go and plug that into the formula. That's going to be 8,710 joules is equal to the mass, which is given to me as 100.0. Let's try that again. 100.0 grams times the specific heat of water, which is 4.184 joules per gram Celsius, right? It's not kilojoules per gram Celsius, but joules per gram Celsius, times delta T, which we kind of don't know yet. So I'm just going to leave delta T in there like that. Let's go ahead and isolate delta T as a variable here. Actually, before we do that, there's one thing I need to go back and actually double check. Please do note that this one did say that there has to be some amount of energy that is released as well. And I forgot to go over this on the previous one, but when we talk about releasing energy, that's giving out energy. And what do we say about the sign of Q when it has to be released? Well, actually, it should be a negative sign. So when I plug in this value, I really should be using negative 8,710 joules because energy is released. We're losing that energy. So that kind of changed our problem just a little bit, but again, in terms of doing the math at this point, nothing's changed. So we've solved for delta T. So we go ahead and isolate that by dividing all the sides, or at least some of you might like seeing it this way. So let's change it up a little bit. Let's try this one more time. Delta T, that's going to equal to whatever every other number is divided on the left side. All right, so that gives us negative 20.8 degrees Celsius. All right, for those of you who aren't really sure what's up with that unit, right, first of all, it is a change in temperature, so it needs to be a degrees Celsius, a temperature unit. But also, right, joules, that's there. Joules are here. They're on opposite sides of the equation. Those are going to cancel. And then grams here on the bottom, or sorry, this on the top, divided by grams here on the bottom of that expression. Those will cancel. So what you have left is basically degrees Celsius when you do isolate that on its side. So delta T here is 20.8 degrees Celsius. And then to finish it off, right, remember that this is the same thing as saying final minus initial temperatures is equal to, I'm sorry, it's a bit negative, negative 20.8 degrees Celsius. So then you end up with this expression, but of course you have to finalize and get the final temperature. So plug in what you have here. That's going to be TF minus a 45.0 degrees Celsius, which we just solved for. That's still equal to negative 20.8 degrees Celsius. And then solving for your final temperature. All right, go ahead and rearrange and solve for that. You end up getting a value of 24.2 degrees Celsius as your final temperature. And that should make sense, right? Because we did give away water. We know that it started at 45 degrees Celsius. It released energy, so it's going to cool off. So it goes from 45 down to 24.2. It's always a good double check to make sure that math worked out. Because sometimes if you forget this negative sign, like I was about to do earlier, right? Forget that to start, you end up with an entirely different number, which does not make any sense, is not consistent with what you should be getting. All right, that'll do it.